Okay, here on the screen, I have what we were busy doing last week. We have we had arrived at this question, and because it was the end of the time, we ended up in this complication here that it's not very clear. And I was wondering, perhaps we should explain that more clearly before we move on to other types of problems with alcohols and so on. So what was that all about? It was they were giving us this compound here. It's a halogen alkane. You see where the bromine is attached to the second carbon. It's a 2-bromopentane. 1, 2, 3, 4, 5. Yeah, 2-bromopentane. And they were asking, give the reagents and conditions necessary for this, for the conversion of this compound into a mixture of alkenes. And we had said that it has to be in some kind of hydroxide dissolved in ethanol. These are the conditions for this elimination reaction, from which a small molecule comes out. In our case, since we have, this is a bromoalkane, that will be hydrogen bromide. And what remains is actually an alkene. And the name of this type of mechanism is elimination. Now, in the third question, they asked us to draw the skeletal formulae of the 3 alkenes produced by this elimination reaction. And skeletal formula for this alkene. So because we said it very fast and it's very unclear, I thought maybe we should do that like more analytically. So I prepared another page here with lots of space so that we can. So here is our 2-bromopentane. Okay, here it is. It's the displayed formula and the skeletal formula, but let us work with the displayed formula of this bromoalkene here. Bromoalkane, sorry. So if this is to undergo an elimination reaction, it will, what is the ion of interest that will, that we're going to use in our mechanism to see what exactly products are going to be produced out of this reaction. And we remember they asked for 3 products. Now, which are these 3 products? Now, what is, we have this ion, the hydroxide ion from the sodium hydroxide in ethanol that we have. So this hydroxide here now will attack one of the protons of a carbon which is attached to the carbon next to the bromine. So what does it mean? It means that this can attack either this hydrogen here, because this hydrogen, this proton, is attached to this carbon which is next to the carbon where we find the bromine atom. So either this proton here from this carbon or this proton from the other carbon, because this carbon is also next to the carbon that is linked to the bromine. So it could be this carbon, it could attack this proton, one proton from this carbon, or a proton from the other carbon. So we have 2 products already, as we can see, that could be possible results, a possible alkene that will form out of this elimination reaction. And what is the mechanism here? Let us remind ourselves of the mechanism of this elimination reaction, because very often they ask to write down the mechanism, and we need to write down to show all the curly arrows and all the pairs of electrons, like these things here. These have to be shown in this hydroxide ion. Okay, so one thing now is that say that this hydroxide ion attacks this proton, picks up this proton, in other words, and what happens there? So one, actually, let's show the curly arrows correctly now, because we need to, the curly arrows must be shown properly. So let's remove all these unnecessary lines that they have drawn there. Okay, and all right, so we have to show this arrow this way, starting from the middle of the pair of electrons and ending up at the proton here. And so if the hydroxide ion attacks this proton, what happens? the pair of electrons of this bond between carbon and this hydrogen will become a double bond with the other carbon, and at the same time, this pair of electrons will move to the bromine atom that will be eliminated as a bromide ion. So what will be the product, in other words, out of all these stories? So we'll have here, remember, this will become a double bond and this bromine will come out. So what we are left with, 1, 2, 3, 1, 2, 3. Here there will be this double bond, and then it's the other two carbons. I hope I got it right there. 1, 2, 3, 4, 5 carbons altogether. Okay, so hold it now. We need to add also the hydrogens. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3. And of course, we'll have the bromide ion that will come out of there. Obviously, the proper reaction, if we write the proper reaction, that will be in the form of a hydrogen bromide, okay? Because remember, what am I saying? Sorry. Nitrogen bromide, the salt, because it will react with a sodium hydroxide. So I'm saying this will be, yeah, hydrogen and now. All right. Okay. So okay, now so the product, if in other words this hydroxide attacks this proton from this carbon, we'll have this product here. Now, what is very convenient for us is when we have a double bond like an alkene, is to show it in this configuration, because then it helps us with various isomers that might be possible. And in this case, we do have isomers, stereoisomers. So what do we have here? If we look the carbon here on the right hand side, this is a hydrogen, so the one will be a hydrogen, the other will be a methyl group here. Let's write it like that so that we can see it clearly. And on the other side, again, we have a hydrogen, and then we have all this other alkyl group, which is actually an ethyl group. So we have again here hydrogen, this hydrogen, and this alkyl. Let's okay. Let's write it as R2, 2 meaning that it has 2 carbons. And this, I could write R1 instead of the methyl, but anyway, that is short, so it's not a big problem. Now, as you can see here, you see this, obviously, there is a case of, this could have, could appear in the other isomer. This is the cis isomer, but we could have also the trans isomer, which means this could be also of this form. If we exchange the order of those two, or of those two, it's still the same. This would be here the methyl and here the hydrogen, and this, if they stay as they are, you see that this is the cis and this is the trans isomer. These are 2 isomers. So these already are the two isomers that they are asking for in this question. Draw the skeletal formulae of the 3 alkenes produced. So these are 2 of the 3 alkenes already produced. So we need to add in the boxes the skeletal formula. But let us see also the third alkyl product that is possible to come out of this reaction. And the third would be if this hydroxide ion attacks this the hydrogen or the proton from this carbon, the other carbon, not this carbon. So what would be the case then if it was reacting, it was attacking the other proton? Let's use the same drawing again. But now this time, hydroxide attacks this hydrogen, this proton. Okay, so it picks it up, comes out, and what happens? This pair of electrons now will form a double bond here between these two carbons. And at the same time, this pair of electrons from this bond between carbon and bromine, this pair of electrons will come out with a bromine ion again, a bromide ion. So what will be the product in this case? Now we'll have a double bond. Sorry, I'm losing my voice. Now the double bond will form here between the first and the second carbon. So what will be our product here? Let's write it up there. And another 1, 2, 3, 4, 5, because it's a pentene. Okay, how many hydrogens now we have? Now 1, 2, 3, 4. 1, 2, 3, 4. Another hydrogen there, another 2, and another 3 there. So we see now this is another product, another possibility, which is the third alkene that's possible. And let's write it in this configuration with a double bond here in the middle. And what will be there? The two substituents of the first carbon, this will be 2 hydrogens, and the other 2 will be 1 hydrogen, and the other substituent is all that, which is a propyl actually. Let's write it as R3 because it has three carbons. It's a propyl group. So you see, this is the one alkene that could be produced if the hydroxide ion attacks this proton instead of that one from the other carbon on the left-hand side of the carbon that is attached to the bromine. So that is why we have all these products here, these two isomers, and this which has the bond, the double bond between the first and the second carbon. So now, but they don't want us to show these alkenes in this form. They want us to show the skeletal formula of these 3 alkenes. So I hope you remember what is a skeletal formula. This is a skeletal formula that shows zigzag shapes at the corners of each of these lines. Is a carbon, but we don't draw the carbon or the skeletal formula. So how could we draw these 3 alkenes now? The first one where the bond is at the end, in other words, this last one where the double bond is at the end, at the last carbon, we can write it here on top. How would it be? 1, 2, 3, 4, 5. Remember, it's a pentene. 1, 2, 3, 4, 5, and the last is the double bond. So that would be the skeletal formula for the alkene where the double bond is at the end. And here we're gonna draw the skeletal formula of the other 2 alkenes, the 2 isomers. We can draw here the cis and here the trans, simply because I have here the trans formula of this pentene that we have. Okay, so here let's draw the cis. This, which is this one, This is the cis alkene, and this is the trans. The trans, where the 2 alkyl groups are at opposite ends. All right, so cis, could be 1 carbon, 2, 3, 1, 2, 3, 4, 5. So here is a double bond, and these 2, you see, are in the same, on the same side of the double bond, because it's supposed to be this is stereoisomer. And here the trans, this part has to be down now because it's on the other end of the carbon. And 1, 2, 3, 4, 5. It's a double bond in here. All right. So this is how we draw them. I hope this is understood. All right. Now, let us move on to another problem that we leave now the halogen alkanes and we go to other things. And this one involves alcohols, as we can see. All right. So where is this now? Alcohols. It's from The structure, yeah. It's from, it's a recent exam paper, isn't it? From this year. The structures of this, hold it, what's that? Of V and W are shown. V and W. Name the class of compound that V and W each belongs to. Well, obviously these are, we can see this group, the hydroxy group. Obviously these are alcohols, okay? But these are not the same type of alcohols. If you notice very carefully, let's make it bigger. Sorry, it's tiny. Yeah, it's much better. You see, okay, here the hydroxyl group is linked, it's connected to the last carbon, as you can see it. You see 1, 2, 3, 4. 1, 2, 3, 4 carbons. With the hydrogens, 1, 2, 3. So this is actually the V. It's a primary alcohol, isn't it? So here, what is the class? Because they talk about the class of this compound, we have to say that this is a primary alcohol, not just alcohol, but a primary alcohol. So the V is a primary alcohol. Or how else do we symbolize it? Primary, like that, primary alcohol, first class. Now the W though, look at this carbon, it's connected to 3 methyl groups here. So we have a carbon and 3 methyl groups, which means this is a tertiary carbon, and this is called a tertiary alcohol. So its class is the class tertiary alcohol, or third degree alcohol. Okay. V and W now. V and W both react with sodium metal. Oh, actually, I must tell you that they do love these questions with the sodium metal, where the alcohol reacts with sodium metal, because they want to see if you understand which bond is going to break in the alcohol. Write an equation for the reaction of V with sodium metal. V, where's V? Okay, so this is the alcohol. This, we need to write the reaction. C and another. There it is, the alcohol. By the way, how many carbons do we have? 1, 2, 3, 4. Okay, butane, butanol. All right, so write an equation for the reaction of V with sodium metal. Okay, let's write here the sodium metal. And what is the result? By the way, we need to know which bond is going to break, and also another important aspect from this reaction is the production of hydrogen. Okay, so of course we'll have the hydrogen gas produced, but look at this, I don't leave enough space with my big letters here. Okay, so what happens here when it reacts with sodium metal? It's the bond between oxygen and hydrogen that breaks, because usually in other reactions that we see, it is the bond between the carbon and the group here that breaks. But in this case, we need to be very careful. It's this bond between oxygen and hydrogen that breaks, not between carbon and oxygen. So the hydrogen is going to be removed from here, and it will be replaced with a sodium. So let me continue this reaction here now to write the products. So all this is going to stay the same up to the oxygen. 3 and another that, and this part, and here instead of hydrogen we're going to write the sodium. And of course we must not remember the production of hydrogen and gas, hydrogen gas. All right, to balance it now we need to have all the others are fine. So and by the way, this is actually an ionic compound here, with the sodium being the positive ion, and this, all that is a negative ion. And this is what we need to write the equation of the reaction. We just need to show that we understand that it's the bond between oxygen and hydrogen from the hydroxyl group that is going to break, and the hydrogen is going to be replaced with a sodium. the sodium metal, and the hydrogen will be produced as a gas. All right. That's enough here because we need to move. Now let's see. The same now question continues. Still links to these alcohols that we had, the V and the W. Now name a reagent used to distinguish between V and W. Remember, the V was the primary alcohol, isn't it? And the W is the tertiary, isn't it? Yeah. Here is the V, which is the primary alcohol, and this is the tertiary. And as always, when there are tests, they are going to ask questions on the tests, and we need to be aware that how do we test alcohols on whether they are, how do we distinguish the tertiary alcohols from the primary and secondary? So this is the way to distinguish is using, you remember, it's this test that from the oxidation of the alcohols. If we use the oxidizing agent, which is dichromate ions, which is the oxidizing agent, we can test if an alcohol is tertiary or something else. Because if we use potassium dichromate, let's where's the potassium dichromate, like that, which is our oxidizing agent. What happens is if we add our alcohol in some solution, acidified solution with some acidified solution of potassium dichromate, what happens if the alcohol is, this is the color, by the way, of the dichromate solution, this yellowish, that is, in other words, before we put any alcohol in. But if we put now in the solution some a primary alcohol, the primary alcohol will react with a dichromate, and it will change color to green. So here I've added this picture here that shows us that primary alcohols will react with a dichromate, and they will produce we are going to see a green solution, the change in the color from yellow to green. If we place a secondary alcohol, again, we're going to see a change from yellow to green. But if we place a tertiary alcohol, and one of our alcohols here is tertiary, there's not going to be any reaction, and this will stay the same color of the dichromate, like the color of the reagent. There is not going to be any reaction. So this is a way to distinguish if an alcohol is tertiary from the other two, which could be primary or secondary. So name a reagent used to distinguish between W and V, describe any observations. So the reagent is the potassium dichromate, but acidified though, acidified. Here we can just write the dichromate ions, there's no need to write the whole thing. And we need to remember that this by itself is like yellowish orange, like this type of deep yellowish orange. How can I describe this color? Yellowish orange, maybe. This is the color of this reagent. Then if we add the alcohol V, it will be oxidized. So it will be oxidized, and because it will be oxidized, which means it will react, we'll see a change to green, from this yellow-orange to green. This solution will change into green. But if we add the tertiary alcohol, we'll see no change, no reaction. That means no reaction. No reaction, and no change, because we're going to see no change in color. No change in color, which means there's no reaction, obviously. That should be first. We see no change in color, which means there is no reaction taking place. The previous case, we see a change from yellow to green, which means there was a reaction, an oxidation reaction taking place. And that's the observation. That's enough, okay? So you see, whenever there is a test of something, we need to know it, to know how to test. We need to know the reagents. We need to be able to explain what changes we expect to see if there is something present, and so on. Yeah. So, and we need to remember that this is actually the oxidizing agent, okay, which means it is reduced itself. All right. Now, what else? Let's do another problem. This one, yeah, if I remember correctly. Let me find my paper here. Which is from 2016 again. Yeah. Here, as I see from my notes, it's actually a mix of various questions from different parts of organic chemistry. Let's see, but they're small and easy questions. In each section of this question, choose the answer or answers from the options listed. 6 particles are listed. Which are these 6 particles? This is a plus there. It doesn't show very clearly, but there is a plus there. And this is also a plus. Identify 2 particles produced during the reaction of methane and chlorine in the presence of UV light. 2 particles produced, if you remember, this is the formation of free radicals of, with the example of chlorine in UV light, where the chlorine molecule splits into 2 of these free radicals, isn't it? So free radicals, we were looking for free radicals, and identified 2 particles that will be produced during the reaction of methane with chlorine. Okay, so obviously there's one. This is one of these particles, free radical. It doesn't matter if we have this dot representing 1 electron to the left or to the right. Both are acceptable. And what other particle can be produced if one of these reacts with methane? It could be this one. This can be a product as well of this reaction. So here is another particle. So those 2 particles. In other words, whatever looks like a free radical. Okay. This is wrong, actually. We don't find it in this reaction. Okay. Next, identify 2 particles produced by the heterolytic fission of a bond in chloromethane. So now we're looking for heterolytic fission. These free radicals are produced through homolytic fission, if you remember. But now this, let's write it here, homolytic fission, to remind us that there are 2 types of fission. Free radicals are formed during the homolytic fission. Now, identify 2 particles produced by the heterolytic fission of a bond in chloromethane. Okay. Well, it could be, okay, this one, this chloride ion could be produced. This could also be produced like ions. We're looking for ions. This could be produced. And yeah, that's it. Let's check. Yeah, that's it. All right. Okay, they have the plus on the other side. Fine, let's do it the way they present them there, but it's okay. They would both be acceptable, actually. That's fine. Okay, so those 2. So we said this in the circles. All right. Now, question B. 7 reaction types are listed. Oh, it's 12 o'clock. Sorry, we have to stop again. We can continue next week again with all sorts of other things. Here you can see I put pictures of other tests again. You can see that they involve tests as well. All the tests, you need to learn them by heart. Anyway, we need to continue next week though, eh? So keep well, eh? So until next week again, until we meet again.